how much further is it to the sun than the moon? In fact, you can answer this question very simply with the power of mathematics. It's one of those remarkable strokes of genius almost that enables you to hold the entire universe in the palm of your hand, almost be able to measure all of these distances, even though obviously you're not going to travel there to any of these bodies, but nevertheless you can understand all of these relationships. A remarkable indication of the power of pure mathematical thought. And the key to performing this determination is the configuration of heavenly bodies that I have indicated here, which is the one corresponding to half moon. You see the moon, half of the moon is lit up by the sun, the other half is dark, and in the configuration I have drawn here, when we standing at the earth look up at the moon, we see precisely half of it being light and half of it being black. So this is a half moon. So the important thing about the half moon is that creates a 90-degree angle in the sky. So a right angle triangle is created because it's precisely what it means that it's a half moon. You know, that we are looking at our line of sight is perpendicular to the line from the sun to the moon. So that creates this 90-degree triangle, and then we can measure the angle between the sun and the half moon. I mean, both of those objects we can see in the sky, and we just have to measure the angle between them. This is only the one and only measurement we need to perform in order to master this calculation. So we just look at those two things, put our protractor there, and check what so and so many degrees. And according to Aristarchus, who did this more than 2,000 years ago, he measured the angle as 87 degrees. You know, is not very accurate, but in any case, you can measure it. And then it's a simple matter to determine the ratio of these two sides. We can say, for example, let's take the distance from the Earth to the Moon here as the unit length. That's what I marked in yellow. This is length. Let's call that 1. And then how many times that is the green dashed length here. That's the one from the Earth to the Sun. And that will come out as about 19 according to this, with the trigonometrical calculation here. Because I have my right angle triangle, I just have to take the cosine of the angle and I get the ratio of these two sides. So 90. You know, this is the value given by Aristarchus. He gives an interval around 19, which is a very poor estimate indeed, and it's much further actually to the sun, but whatever. The interesting thing here is not the precise numbers, obviously. It's not like you're going to actually go there to the sun, so you don't need to know it for that purpose. The interesting thing is mathematically the procedure is absolutely accurate, and it's just a remarkable to realize that you can measure the heavenly distances which using nothing really. You just a simple measurement of one single angle. You can stand in a field and just figure this stuff up. No, Wikipedia or computers or anything like that. You just a simple calculation. This is all you need. So that's the power of mathematical thought right there. And Aristarchus, in fact, continued his investigation and determined also, for instance, the size also of the moon relative to. So I'm going to keep using this color coding convention that I made up to make these pictures clear. So I'm using yellow for unit of measurement. That is to say, we don't actually know how long this yellow thing is, but we call it just 1. That's my unit of measurement. And then I use red for things I don't know, and I use green for things I do know, which are the angle here. I can measure the angle that I marked seen from the Earth is the angular size of the moon. It takes up, like maybe 2 degrees or something worth of, the size of the moon takes up a certain angular size. And then we have this. I know that there's a right angle over there because of the diameter of the moon stands perpendicularly to the line of sight here. That's how we are conceiving the situation. So those two things are known, and then I draw in this dashed green, means the thing that I can figure out from what is known. So in this case, knowing this angle and knowing the yellow side, I could then figure out the remaining dashed one, again by a trigonometrical calculation, because it's a ratio of sides in a right angle triangle. I know the angle, so I can figure out. It's a simple trigonometrical matter to solve for the last one. So that I can figure out the dashed one. Okay, that's so now I know then also the size of the moon relative to this. Here, if I try to do the same thing for the sun, it wouldn't work, because now I marked instead the angle red here. It's not green, because with the sun, you can't really see the edge of the sun. You can't really measure precisely where the sun starts and ends. You know, it is such a, you can't stare directly at it, and it's kind of fluid boundaries there because of its so powerful. So you can't actually measure. So you couldn't determine the size of the sun in this fashion with the same method as for the moon. But there are nature has provided for us precisely the circumstances we need to nevertheless determine the size of the sun, namely the phenomena of the solar eclipse. And the solar eclipse is when the moon obviously stands between us and the sun, blocking out the light from the sun. And a very remarkable fact is that at such occasions, the moon precisely blocks the sun. So it's as if it had the exact same size as the moon. I mean, in relative size, apparent size. Of course, the moon is closer. So, but you know, the visual size of both objects at this time are identical as we see in these pictures. So, it's this is just really a very remarkable fact, and something that in ancient times we would have thought this is really a gift from the creator of the heavens, that he has made mathematics easy for us by making these kinds of patterns, almost asking us to study these distance relations, whereas in modern terms it's just a pretty amazing accident that these two bodies happen to look exactly the same at the time. Anyway, so be that as it may, the fact is that at the time of solar eclipse, the moon exactly blocks out the sun. It's not too big, it's not too small, it exactly fits. So therefore we have this kind of situation which I have drawn over here, that the moon precisely fits in this little cone of sight that goes from us to the edges of the sun there. So I have here previous. So as usual, I'm using the distance from the Earth to the moon as my yellow unit of measurement. That's the same as I've been doing before. The size of the moon I have already determined from a previous slide. Likewise, the distance to the sun I also determined previously. That was the 19 times the distance to the moon that I already determined before. Now that I know those matters, these green and yellow, I can easily compute the dashed green one, the size of the sun. So now I can determine the size of the sun. So because of the similar triangles here, obviously the little configuration with the moon here is similar to the big configuration with the sun. So using similar triangles, I can find the size of the sun. And we can also, there are lunar eclipses, of course. So instead of the moon blocking the sun, we now have a situation where the Earth's shadow is cast upon the moon, so that the moon is blocked and becomes dark due to the shadow cast by the Earth. And in such a situation, it happens that the size of the Earth's shadow is about twice the size of the moon itself. Oh, so it's a little bit less clear cut than in the solar eclipse case, but you can see in these pictures that this shadow that is coming in and covering the moon, it appears to be more or less twice the size of the moon itself. It looks to be the dark area appears to be that of a circle twice as big as the moon, more or less. So that means that we have a situation rather like this. That is to say, so I have here drawn the cone of light from the sun. That part of the light from the sun that is blocked out by the Earth is contained here between these red lines, and then the moon, you can see, fills up precisely half of that space. So you could fit two moons in there. That's what we just argued in the previous slide. So if we look at this configuration, we already know the size of the sun and the size of the moon from before. But now I'm going to use a new unit of measurement for my further calculations here, which is this unit, the yellow one that I've drawn here, which is the distance from the moon to this the end of the cone of sight, the end of the shadow cone of the Earth. So I'm going to use that as a new unit of measurement. Nevertheless, I know these green ones in my old unit of measurement, but nevertheless I know the ratio between these green ones, which is what I need for the purpose of this calculation, because what I need to compute here is the dashed green length, which is obviously obtained by similar triangles again. This is the one with the yellow, and the moon is the same as the dashed with the green part of the sun there. So those two the similarity, those two triangles enable me to compute this dashed length. So, and then now that I have computed the one that was dashed in the previous image, that I can now make that solid, because that I figured out now. And then I want to figure out this new dashed length, which is not, instead of starting all the way down at the right end, I'm not going from the sun to the from the moon to the sun. So how can I find this dashed one, given all these previous things that I know? Well, clearly I just take the big green one that I just computed, and I subtract the yellow, and then I get this dashed one. Okay, so that one is also known, so I can fill that one in solid now. And now I want to know the distance from the Earth, center of the Earth, to the moon. That's the dashed one here. How can I determine that based on the previous knowledge that I have, the previous green ones? That is determined by the last green one that I did, shaded in here. The green, that was the distance from the sun to the moon. But I determined previously on the very first slide that the distance from the Earth to the sun is 19 times the distance from the Earth to the moon. So therefore, this last green piece that I shaded in, this last solid green one, I can split into 20 parts, and it's going to have 19 parts. It's going to go to the sun and 1 part to the moon, because that's the proportion that we established earlier. Obviously, the picture is not to scale, but you get it. So therefore, I know how much this dashed one is, because it is 1/20th of the total, because it's 19th part of the distance to the sun. So I can make that also solid, but then I can determine the size of the Earth here is now the dashed one, and which I can determine through the similarity of triangles, because now I know the distance from the Earth all the way to this cone point on the right, and then also the size of the sun is determined from before, and that's distance from the cone point on the right. So now I have two triangles, one for the sun, one for the Earth, diameter of the sun and diameter of the Earth, and as my two similar sides, as well as the distance going from their midpoints up to the cone point. So that those similarity of triangles there enable me to determine the size of the Earth here. Then I can use the size of the Earth, the diameter of the Earth, as my new unit of measurement. It's just a unit conversion from the old unit that I had. And if I use that unit, then I can express all these other lengths in terms of that unit. So basically, I have determined the distances and sizes of the sun and the moon in terms of the size of the Earth. This is the end of this treatise by Aristarchus. He determines all of these matters, distances and sizes of the sun and the moon, in relative to the size of the Earth. So, remarkable accomplishment by the great Aristarchus. Very interesting applications of trigonometry. Soon thereafter, you have Eratosthenes determining what is the size of the Earth then. And that was the unknown in the previous calculation. We only had the size of the Earth was just assumed as a unit of measurement, and we didn't know how many, meters or anything like that. But nevertheless, we used it as a ruler for measuring the rest of the heavens, so to speak. Well, Eratosthenes then supplied the missing link, the size of the Earth itself, and he did it in this fashion. He considered 2 points on the Earth's circumference here, Alexandria and Sienne, in Egypt, and they are located, as you can see in this map here on top right, they are lying more or less on a north-south line there, more or less aligned in that fashion. And the measurement goes like is in the manner shown over here with these little guys standing around here on the left. So if we look at this picture with the well here, we see that the rays from the sun are coming straight down and going straight into the well. So we can see the bottom of the well there is going to be lit up by the sun, and then we know that the sun then is standing straight above our heads. It's absolutely perpendicularly above the surface of the earth. That is also shown over here in this diagram of the earth over here, where you see the rays from the sun are coming in, going through the well, and in principle they're heading straight for the center of the earth. Is what it means. Another way of saying that the sun is straight above your head is that the ray is hitting the midpoint of the earth, if it could travel that far. Meanwhile then, when that occurs in Syene, that's then in Alexandria further north, the sun is going to be not straight above your head anymore, because you can tell here you're pointing in a different angle, your heads, if you're standing there. So then you you can measure the deviation from how much off it is from being straight above your head, and that's what this guy is doing here on the far left with the pillar there, determining how much what the angular difference is between straight above and where the sun actually is in this occasion. So that angle then, as we see in this diagram on the bottom right, knowing that angle that we can measure there, staring at this shadow of this pillar and so on, that angle is the same as the angular distance between these two cities as seen from the center of the earth. And because of the parallel rays from the sun, you easily see that these angles are the same. So that means basically this is telling you how big a part of the earth's circumference the distance between these two cities constitutes, how big a part of the total. So if we know all the way around, obviously it's 360 degrees, and so if this is 10 degrees, we have to multiply by 36 to get the full circumference. It's 1/36 of the full circumference, or so it's like that. So therefore, we send our camels now, like it says here in the picture, walking from one city to the other, and determine how far that is, and then just multiplying by the appropriate amount to get the total circumference of the earth, because we know how big a portion of the total circumference of the earth is at stake here. So therefore we have determined the size of the earth, the circumference of the earth, or radius, diameter of the earth, the same. If you know one, you know the other. So that's very powerful. Now, putting all these results together, we get this. We know now the size of the earth, the diameter of the earth, in terms of how long it would take to go with the camels. That's what we measured in the previous slide. And putting that together with the Aristarchus measurements, which determine all the heavenly distances in terms of the sun, that means that, we determined all the heavenly distances in terms of the size of the earth. Now that we know the size of the earth, as far as camels are concerned, we also know how long it would take to go with camels all the way to the sun, and so on. So everything is known now in ordinary units of measurement, like meters or feet or whatever you like, or how many days worth of camel ride or something like that. So pretty amazing that we can figure out all these things just sitting on Earth. We know exactly how big the sun is more than 2,000 years ago. So that's remarkable. So now I want to say something about the cultural context of these two determinations of these heavenly distances. So for this purpose, I have given here a simple timeline of classical Greece. So we have in the top left is the beginning in Athens was once, of course, the center of all culture and intellectual life in the classical world in the 4th century BC. Then we have these three generations: Socrates, Plato, Aristotle, obviously the great philosophers, and so that was the pinnacle of the Athenian cultural tradition. But at a certain point, the importance of Athens declines, and Aristotle leaves Athens in this year, minus 343. So BC, I indicate these BC years with the minus. So he leaves to become the teacher of Alexander the Great, the so-called Alexander the Great, in Macedonia. So the young Alexander is training to become obviously the great conqueror, and soon thereafter he goes on his great conquering spree. Alexander the Great conquering, all around the Mediterranean. He's just conquering one land after the other and so on, and he founds various colonies and things, including the city Alexandria in Egypt. And then that, in effect, takes over as the new center of intellectual life. So Alexandria is going to be the new center of philosophy, science, mathematics, and so on, taking over from Athens, picking up the torch, as it were. And so we have there, among others, Euclid and so on, being very important people in that place. So the important work is taking place there now instead. So it's useful to keep this in mind, that Aristotle is the sort of the link that is you can remember this transition by means of the fashion in which Aristotle stands with one leg in each, so to speak, in this fashion. So, but now back to the this context is useful for understanding these two measurements of the heavens that I described. So we had Aristarchus and Eratosthenes who provided these two measurements, and in fact Aristarchus they belong to one of these two Greeces, so to speak. Aristarchus belongs to the old Greece, to basically Athenian Greece, the Greece of Socrates and Plato and that kind of tradition. And he's from Samos, which is not Athens as such, but nevertheless you can see here it's close to the classical Greece, so part of classical Greece, the old Greek. And so Aristarchus belongs there, and whereas Eratosthenes is born in Cyrene, which is in the northern coast of Africa here, just like Alexandria is also on the northern coast of Africa, Egypt. So Eratosthenes is born in New Greece, Hellenistic Greece, the Greece that has recently been conquered by Alexander. So that's great. Even though they are only a generation apart, nevertheless you can see that there is this is a crucial generation that shifts. Many things shift between them, and indeed, in my opinion, you can also see this in their very mathematics. This transition, because I have indicated over here the basic distinction in character between these two sides of Greece, the old Greece and new Greece. So we have a representative of the old Greece would be Plato, is the pinnacle of that tradition, and Plato in Athens then is very much a highly idealistic philosopher, an armchair philosopher, as it were. He is convinced of the power of pure thought. He has a contempt for working with actual specific real world physical experiments and measurements and such things, and thinks that real mathematics is very abstract, very pure, and so on. And so he's obsessed with it, and that's why also in this painting by Raphael, the School of Athens, he's pointing to the heavens. He's very much head in the clouds kind of guy, Plato. And then there's a kind of transition with Aristotle, who is, although Aristotle is a student of Plato and still grew up in the Athenian Greece, he nevertheless, was the one who left and was the one who is ideologically aligned more with New Greece, with the Hellenistic Greece, New Empire. So, and you can see his hand, on the other hand, he's more, whoa, stay on earth, more concerned with the practical world around us, not with the heavens so much like Plato. So that is the emphasis of Aristotle in that fashion, more concerned with the mundane world of ordinary people. And isn't that exactly also what we see in the trigonometric proofs when you think about it? So Aristarchus is very Platonic, as it were, in his determination. He determines the sizes and the distances of the sun and the moon, but it's extremely impractical, obviously. It's just like a fanciful uh, exuberant fantasy almost that you determine these distances, and you're not going to use them for anything. Obviously, how could you ever? It's not like you have a spaceship or anything that you can make any use of these numbers. But it's just cool to do it. And even his actual numerical measurement was completely off. I mean, it's like he didn't even care. He was just putting some numbering for the sake of illustration. But really, he was just wanting to show these cool things, how you can really sit in an armchair and just figure out master the entire universe without really engaging, dirtying your hands with anything. So that's a very much in line with the classical Platonic ideal of a pure mathematician, philosopher type of investigator. So on the other hand, you have Eratosthenes, who's doing something a lot more concrete, a lot more hands-on, working with actual measurements of a specific distance within Egypt. You have to actually run your camels so and so far and all these things. So that's more of an Aristotelian type of empirically oriented investigation. And you can understand likewise the fact that these new uh, territories, the northern African coast and so on, were all conquered at this time to Alexander the Great. You might imagine that that brings with it a shift of emphasis to more about understanding the size of the earth becomes more relevant in this context. When you're conquering land after land after land, you start thinking, how much land is there? How much is there to conquer? How big is this place? How much can I conquer and steal? So, that's a type of question that arises more in that hands-on conquering kind of mindset than it does in classical Greece. I mean, people didn't care about the world around them; they didn't care about the guy down the street, let alone how far it was to some. What did they care? They were philosophers. They were just living in the clouds in Athens, so they didn't care about the size of the earth. But when you're running an empire that's massive, you're going to start to care about the sizes and distances of things, and that's why that arose in that context instead. So that I think is a beautiful illustration then of how these particular trigonometrical investigations are reflective of general cultural tendencies at the time. Thank you.